Many practical problems require the movement of some commodity from one location to another. In Chapter 7, we'll look into this type of problem and model it with weighted directed graphs. For example, an oil company must move crude oil from the oil fields to its refinery. Another example would be a long-distance telephone company wanting to move messages from one city to another. In these type of problems, we're going to define transportation network, flows, and cuts. Here's the definition of a transportation network. It is a weighted directed graph satisfying three conditions. First one and only one vertex having no incoming edges. And we're going to call that vertex source. Number two, one and only one vertex having no outgoing edges. That's called a sink. And the weight assigned to each edge is non-negative. Here's an example of a transportation network. This is a weighted graph, and each edge has a direction, so it's a weighted directed graph. And notice the two special vertices. Here is the source, a vertex having no incoming edges, only one. Number two here, satisfying the second condition of the definition. A vertex having no outgoing edges, that's called a sink. And we have only one sink. Notice that the weight of each edge is non-negative. You could have weight 0. In this definition, we'll call each edge an arc. And the weight of an arc will be called capacity. Now let's define flow. A flow in a transportation network is a function f. It's a function of the arcs of the graph of the network. And here are two conditions. One, the value of the function at each edge must be less than or equal to the capacity of the edge, and it has to be also non-negative. Number two, at each vertex, the total flow out of the vertex must equal to the total flow in, and the exception is at the source and at the sink. Let's take a look at this example. Notice that now we have a transportation network. Again, each edge has a number, has a weight, and these weights are called capacities. Now we have a second number at each edge. And these second numbers that you see here in the graph, those are the values of the function at each arc. So for example, the value of the function at this arc is 0. The value of the function this arc is 4. Now, notice that these numbers satisfy these two conditions. The second number is the flow, is the value of the flow at that arc. This is 0 and this is 8, so 0 is less than or equal to 8. And it's a non-negative number. Look at this number 4, so less than or equal to 4. So the second number is always less than or equal to the first number. And the second number cannot be negative. The second condition says that each vertex, the total flow in must be equal to the total flow out. Let's take a look at vertex C, for example. The total flow in, coming from these two edges here, these two arcs, is 0 and 4, so that's a total of 4. And the flow that is going out of the vertex is also 4. Look at this vertex B. The total flow in is 6, and the total flow out is 4 plus 2, that's 6. The total flow into D is 3 plus 2, that's 5, and total flow out is 5. Here's the first theorem of chapter 7. It says that for any flow in a transportation network, the total flow out of the source is equal to the total flow into the sink. Now, this seems to be an obvious statement, but it requires proof. Perhaps some of the flow that go out of the source could get lost within the network. For example, suppose there is a cycle inside the network, and then perhaps some of the flow out of the source will be simply rotating or will never get into the sink. But the theorem guarantees that all the flow out of the source will eventually go into the sink. And the proof of this theorem is on page 361 in the textbook. And you can take a look at the proof. Now, because of this theorem, this flow that goes out of the source and comes into the sink, because it's the same value, we call that value the value of the flow f. So it's the value of the function f on the entire network. That's the definition. And a flow having a maximum value in the network is called a maximum flow. One of the things that we're going to do in this section is to try to find a flow that has the maximum value. And one idea is to begin with a flow and try to increase the flow until there will be no more improvements. Consider a network with a present flow. If we can increase the flow in a path from the source to the sink, then this path will be called a flow augmenting path. Let's take a look at this example here. Here's a transportation network, and currently there is a flow there. Remember, a flow is a function at each edge, and the flow is currently 0. The value of the flow is 0. See, the total flow out of the source is 0. If we add these numbers, these second numbers are the values of f. And look at the flow into the sink. It's also 0. Now, let's try to increase the flow from the source to the sink. One way we can do that is to analyze, for example, this path ACE. Now, currently there is 0 flow going there. Imagine a highway, and currently in this highway there are no cars traveling. Now, if we start adding cars to this network or to this highway, then we can have a maximum capacity of 8 units on this edge, and there's a maximum capacity of 4 units on this second edge. So along the entire path, we can only increase 4 units maximum. Because if we increase 5, we should be able to bring 5 units from A to C, but not from C to E. So we are limited to only 4 units. We can increase the flow along this path by 4. So here is, if we do that, then now the flow here will be 4, and then the flow here will also be 4. So we are able to increase the flow from the source to the sink by 4 units. Now here is another path we can also increase from A to D, going through D. Now the maximum flow we can increase here would be 3, even though on this edge here we can increase up to 9 units of flow. We are limited to only 3 units because of this first edge, this first arc. So the maximum we can increase is 3 units. Here is another path where we can also increase the flow. So currently there's 0 units going in here, there's 0 units going in there, and there are 3 units going here. And those 3, of course, come from this arc over here. But along this path, we should be able to increase the flow. Now I can increase up to 6 units on this edge, on this arc, 6 units on this arc, and 6 units on this arc, because the capacity on this very last arc is 9, and there's currently a value of 3 here. There are 3 units of flow going in through this arc. I can increase up to 6 units along this entire path. Now, take a look at the flow going into the sink. The only two arcs going into the sink are these two here. Notice that this arc here is at the maximum capacity. The capacity is 4 and the current flow there is 4. This other arc, the capacity is 9 and then the current flow there is 9. So there is no more room for improvement, even though I could increase some in some of these arcs, I could increase the flow. For example, along this edge here, along this arc, the capacity is 8, and currently the flow here is 4. So I could increase 4 units along this arc. However, those 4 units wouldn't be able to go out of the vertex C. So by looking at these two edges, these two arcs going into the sink, we can see that we reach the maximum capacity. So it's not possible to find another flow augmenting path. Therefore, this is called a maximum flow. Notice that the total flow going into the sink is 13. If we add these two numbers, 4 and 9, that equals 13. Now, according to the previous theorem, that number should also be equal to the total flow going out of the source. If we add 4, 6, and 3, that also gives us 13. Now let's define cuts in a network. We're going to partition the vertices of the network into two sets. Now this is not related to bipartite graphs. This partition will have the sets S and T. Set S will contain the source, and set T will contain the sink. The sum of the capacities of all arcs from the partition S to the partition T in a cut is called the capacity of the cut. Now this is from script S to script T, not the other way around. Let's take a look at one example. Here's an example of a cut. Notice that script S, that's the set of vertices that contain the source, and set script T, that's the set of vertices that contain the sink. Notice that these three vertices here, A, B, C, are over here, and they include the source. And DE, the remaining two vertices, that set T includes the sink. Now this is a cut, and the diagram of this cut will be represented by this line because we're separating these two groups of vertices. Now the definition of the capacity of the cut is the sum of all the capacities going from this side, script S, to the T side here, script T. Now if we add the capacities going from S to T, we're going to add the capacities of these three arcs right here. It's going to be 3 plus 6 plus 4. That's 13. Here's another example of another cut. This time set S has A, B, C, and D, and set T has only the sink. And that's the representation, that's the graphical representation of this cut. Now let's, what is the capacity of this cut? Well, let's add all the capacities going from the S side to the T side. And that will be this 4 here and this 9. That's going to be 13. Here's another cut. This is from a different network. Now notice that here now we have ACD and set T has BE. And here's the graphical representation of this cut. Now the sum of the capacities from S to T would be adding all these numbers. So here's the cut. All these numbers from edges going from S to T. So that will be this 4. not this 5, because this 5 has an edge going the opposite direction. We want to add capacitors going from this side to this side, not the other way. So we add 4, not 5. We add 6, so it's 4 plus 6, that's 10. And here's another edge going the opposite direction, so we don't add that number 6 here. And here is 9. So it's 4 plus 6, that's 10 plus 9. The capacity of this cut is 19. All right. Let's take a look at again the same transportation network. The capacity of this cut is 19. And here's two questions. What is the total flow from the S side to the T side? Remember, this is the S side, the side that contains the source, and the T side is the side that contains the sink. Let's add the total flow, not the capacities this time, just the flows. So from S to T, we're going to add this number 4. It's the second numbers now, not the 1 here because it's going the opposite direction. So 4 plus this 6, that's 10, plus not this 5, now add 7. So 4 plus 6 plus 7, that's 17. Now let's add the total flow from T side to S side. That will be now this number 1 and the number 5. So that's a total of 6 going from the T side to the S side. Now there is a theorem that says that the total flow from S to T minus the total flow from T to S, that is the value of the flow. And that's theorem 7.2. So let's take a look at this again. The total flow from S to T, that's 17. The total flow from T to S, that's 6. 17 minus 6 is 11, and that's exactly the value of the flow. Look at the value of the flow. Forget the cut. Let's look at the value of the flow. The value of the flow is the value going into the sink or coming out of the source. It doesn't matter because the two values are the same. 4 plus 7, that's 11. Or if you add 3 plus 6 plus 2, that's also 11. And that's the value of the flow. Theorem 7.2 says that the value of the flow is the flow from S to T minus the flow from T to S. Now, one consequence of this theorem is that the value of the flow cannot exceed the capacity of a cut. Now, the capacity of a cut is 19. And so the value of the flow cannot exceed 19.